So let's start off uh, with the discussion on eigenvalues, eigenvectors, diagonalizability, and so on. So, so basically, we'll be discussing eigenvalues, eigenvectors, diagonalizability, and Jordan canonical forms. Right? Right. So we all know the definitions. I guess the basic definitions we are all aware of. We'll be looking at some properties, right? First of all, uh, we can, I mean, these are some straightforward properties, okay? So, so observe that, so lambda, okay, so let A be an n by n matrix. Over some field F, then what can we say about, uh, then what can we say about the eigenvalues of A? Then lambda is an eigenvalue of A if and only if A minus lambda I, right, has a determinant 0, okay, right? And this polynomial, so the polynomial which we obtain when we put A minus x times I determinant, this is called the characteristic polynomial. And so what we can say is that eigenvalues are roots of the characteristic polynomial, right? Or you can say roots of the characteristic equation. Okay. So what are the, so if I say that you have a linear map T or a linear operator or a linear map from T to V, right? A linear map, then what would be the eigenvalues of T? The eigenvalues of T are nothing but eigenvalues of A. So eigenvalues of A and so instead of A, I'll write the matrix corresponding to T, that is same as the eigenvalues of T itself, right? Now observe that suppose suppose that suppose that V is some non-zero number, non-zero vector, right? Right? For which say AV, right, equals to lambda V. What is lambda? Lambda is a scalar in the field F. Suppose this holds. Then uh, then observe that then A times alpha V can be written as uh, lambda times alpha times V, right? What is alpha? Alpha is again a scalar. Okay. What does this mean? This means that alpha V is also an eigenvector corresponding to the eigenvalue lambda. Okay, that is what it means. So whenever you have an eigenvector, a scalar multiple of that is also an eigenvector. Okay. So what we are interested in is that uh, so what we are interested in, we are interested in the we are interested in the uh, in the subspace, right? In the subspace of all eigenvectors corresponding to a particular eigenvalue, right? So what we observed in number 4 is that uh, you take any vector, if so 0 vector will be a eigenvector for every eigenvalue, right? So 0 is anywhere there. Now if you take any non-zero vector, right, which is an eigenvalue, scalar multiple is also an eigenvalue, right? Similarly, if v and w are eigenvectors corresponding to lambda, then any linear combination of v and w will also be an eigenvector corresponding to that eigenvalue lambda, right? So what are we getting? We are getting a subspace of vectors, right? So an eigenvalue lambda, okay, in F, right, is generating subspace, right? Right. So that subspace is called the eigenspace of lambda, right? Now what is our interest? Our interest is in the basis and dimension, definitely, of this subspace, right? So we denote the eigenspace of lambda as E lambda. Right? So we all know what's the definition of algebraic and geometric multiplicity, right? So algebraic multiplicity is the number of multiplicity in roots in the characteristic polynomial, right? In the characteristic polynomial. Right. And what is geometric multiplicity? Geometric multiplicity is the number of, or you can say it is the dimension. It is the dimension of the eigenspace of lambda. So this is what this is. So this is nothing but am of lambda. Okay. So the algebraic multiplicity of lambda, that is equal to this, and the geometric multiplicity of lambda. Right? Okay. This is the definition, and definitely am, the arithmetic multiplicity, or the algebraic multiplicity, is bigger than or equal to the geometric multiplicity. This proof is also straightforward because we'll have to observe that the eigenspace will have a dimension less than or equal to the number of multiplicities the characteristic polynomial, right? All right, so let's look at the proof of why the arithmetic multiplicity is bigger than or equal to the geometric multiplicity, right? So let's say you have a matrix, right? So it's the proof. Let's say you have a matrix A, right, which n by n, right? Uh, and let lambda be an eigenvalue with geometric multiplicity equal to some k, say some k, right? What does that mean? That means the eigenspace of lambda is a span of uh, k eigenvectors, right? So let me call those v1, v2 up to vk. Okay. Now what I do, so by Gram-Schmidt, we can say that this E lambda can be written as span of u1, u2, dot, 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 uk. What is special about these ui's is that this is an orthonormal set, okay? This is an orthonormal set. What does that mean? That means that ui norm squared, right, is equal to 1 for every I, and ui transpose uj is 0 for every I not equal to j. Okay. So this is what, so we can write the eigenspace as the span of orthonormal vectors, right? Okay. So now what I do, now by extension theorem, we can extend this to a basis in Rn, right? Which means u1 up to uk, and then it is extended, say uk plus 1. We are adding additional vectors, and this is a basis of Rn, right? Or Fn, whatever. Now let's take, let's call this matrix, say capital U, right? What is capital U? Capital U is the matrix formed by having u1 as the first column, u2 as the second column, and so on, un as the nth column, right? Now, what can you say about a minus lambda I multiplied with 2? What can you say about this? What will be the first column? The first column would be so actually I should have taken not lambda but some variable, say x. Okay, what would this be? This would be a matrix whose first column is lambda minus x times u1. This is the first column. What is the second column? Lambda minus x times u2, and so on. The kth column would be lambda minus x times uk, right? And after that, it can be any column, right? We in fact we do not bother much about the others, but let's just write them as, say, wk plus 1, right? up to Wn. Okay. Now observe that uh, if you're taking determinant both sides, right? So what would you have? You would have determinant a minus xi times the determinant of u, that would be equal to. Now take lambda minus x from the first row, second row, up till the kth row. That would make it lambda minus x to the power k, right? And then you have the determinant of this matrix whose first k columns are u1 up to uk, and then you have something else. Okay. Okay. But also observe that these wk plus 1, wk plus 2, and up to wn, uh, this has components of x in them, right? Because what is wk plus 1? Is a minus xi, right, acting on u k plus 1, right? So this is a function of x. Okay. So what I meant to say is that there are entries which have x in them. So what does it make it? So we can say that this is lambda minus x power k to some polynomial in x. Okay. Now also note that the determinant of u, since u is an orthogonal matrix. Why is it an orthogonal matrix? Because the columns itself are form an orthonormal set, right? So the determinant can be either +1 or -1, right? But what is this? This is actually plus minus of the characteristic polynomial of a, right? This is the characteristic polynomial, right? So we are expressing the characteristic polynomial as x minus lambda to the power some k times px, right? What does that mean? That means so there are at least k many roots of lambda, right, in the characteristic polynomial in x, right? That, what does that mean? This simply means that the arithmetic or the algebraic multiplicity of lambda is at least k, right? What is k? K is nothing but the geometric multiplicity of lambda, right? So this is how we can show that am will be bigger than or equal to gm. Now we all know this thing, that so we know that the trace is the sum of eigenvalues, right? And the determinant is the product of eigenvalues, right? So in fact, if you have a 2 by 2 matrix, so let A be a 2 by 2 matrix, then what would be the characteristic polynomial of A? CHAX would be equal to the characteristic polynomial, that would be equal to x square minus the trace of A times x plus the determinant of A. This would be the characteristic polynomial. Just observe trace and determinant. This you can easily follow. This you can easily derive from the fact that the two roots of characteristic equation are actually the eigenvalues. Right? So what happens if A is 3 by 3? If A is 3 by 3, then this is written as, so you'll have x cube, right? That is for sure. Some of the roots will always be in the second term, so you'll have trace of A times x, or sorry, which would be x square plus, now look closely, capital A11 plus capital A22 plus capital A33 times x, right? And then in the end you have minus determinant of A. Now might be wondering what is capital AI. So AJ, capital AIJ is the cofactor, right? Cofactor of little aij, cofactor of little aij, right? This is what capital Aij is, okay? Okay. So how can we generalize this? So in general you can say that the characteristics polynomial of x, so let's say n is n, okay? Then this would start with x power n, right? Minus s1 x power n minus 1 plus s2 x power n minus 2 and so on. The final one would be minus 1 power n Sn, that is equal to 0. Or you can say, you don't have to set it to 0. This is the characteristic polynomial. Now you might be thinking, what is S1, S2 and all that. So Si or Sk is the is what? This is look at all principal minors of order can sum them. Okay, so this is the sum of, right? Sum of all, okay, all principal minors, right, of order k. Okay. One more thing. So we have this very popular result saying that if the eigenvalues are distinct, so the eigenvectors corresponding to distinct eigenvalues are linearly independent, right? So if the eigenvalues are distinct, then the eigenvectors will be linearly independent, right? The next result I would like to say is that if Px be a polynomial, right, and let's say lambda is an eigenvalue of A, right, then P lambda is an eigenvalue of P. Okay. So this is the basics. The next we'll look at diagonalization.